Where you live? Building 2, building 3?
Building 2.
2? Because Chris's wife told me that she thought you were in 3.
No,
you're not.
Okay, no. Building 2. In the same building as yours.
Okay, no, I trust it. Just that when she asked me, she said, "Oh no, Ahmed is in building 3." I said, "Well."
Because once I think I saw you getting out of the same building.
Yes, it was. Yeah, exactly. So I trust that you were right, but maybe she got the wrong information. I don't know why. But...
Okay, how are we sending this now?
No, there are 3 people there.
Who else apart from you?
Another Chinese guy.
In building 2?
In this floor, I don't remember his name.
What, she? She?
Yeah.
Oh, really? He's in building 2?
Yeah.
Oh, which floor?
I think 2nd floor.
2nd floor, okay. Well, I'm in 4 and he's definitely not in 4. So he's not in 3 either, right? So he must be the other 2. Actually, I just met my neighbors the other day, and I think they're quite senior people.
Sorry, I noticed that.
Yeah. No, it was Doomsday trying. Yeah.
Hello. Nice to see you again.
Good to see you again.
I promise you are here.
Sorry?
Yeah, you said you would call and
Yeah, take all this stuff, but you don't go to
not this time.
I know, see, when I should go to his office.
Door open, exactly. So either he's talking and he's got the door closed, or he's not.
We wait for the host and Mauricio.
No, Hal said that he doesn't know why he's here. You chair it.
I think we're close to advance. It's not even 4 p.m. Well, 2 minutes to 4 p.m. It says 4:05 here.
No, that's because that's wrong. Yes, but
Yeah.
Yeah, that has a. That 5 minutes belongs to Android.
yeah, that's true.
Hola, Mauricio. Hello.
Yes, yeah.
Las fotos ahí. Y después tomamos una de grupo así para mirando hacia allá para que la gente no se aburra viniendo hacia acá.
There was also last minute editing.
The title, I put a different title because I forgot which title I sent her. Yeah, she told me, that's not the title. Let's say it is because it seems working.
It's working.
Yeah. And there's a pointer here, this one.
It's some sort of pointer. Yeah, it's 2
Telling to sensitive, yeah.
Okay, now I see. And you can,
Otherwise, the most.
and you can disappear it, like.
Maybe it's okay.
After a while,
If you don't move it, yes.
It won't
maybe.
be long, no? Okay, anyway.
Wait a few minutes.
Sure. No
For
problem.
the characters. For the characters. The characters that appear left. Let me see. So, is Andre back?
I don't think that.
No. Okay, so one character is too far away. But there are other characters. Yes. So we have the number of characters is strictly higher than 2, you know. You can identify all of them, all the characters. They are different species. 3 minutes to the characters.
There's somebody walking.
Miguel, I don't think he will come today.
He has
He's teaching.
Oh, yes, he teaches.
Yeah.
Tomorrow? No, he teaches tomorrow.
He teaches on that.
No, he can teach us today on Thursday. He teaches at Jam 1. No, on Thursday.
Miguel is Thursday, today, yeah.
Yes. Like right now, maybe. Also.
He's teaching probably
Yes,
right
yes,
now.
yes,
yeah.
yes.
So yeah, so if you want to make it. Okay, I guess we can start. Yeah, we've got sufficient characters. Sufficient characters. So we'll present you that. So welcome again to the second physical mathematics seminar of the week, second in the week, exceptionally. Today we're very happy to have not countrymate, but almost
Almost continent.
almost country.
Same continent.
Same continent. Sure.
Same portion of the
Same
continent.
portion of the continent. Professor Ivan Arraut from St. Joseph University in Macau, talking us about spacetime and internal symmetries, spacetime dimensionality, and Quantum Yang Baxter Equations. Please, Ivan.
Okay. Yeah, it's a custom, it's a culture here in China.
Sometimes.
Fantastic.
To grab after the talk.
Yeah. Okay. Okay, thank you very much. Yeah, as a Mauricio, I thank Mauricio for the chance to give a talk here. My name is Ivan Arraut. In reality, is a pronunciation, but in Spanish it's Arraut, so it's okay. Arauto in Japanese, if you want to say the Japanese way. And I come. So we met in Japan in the IPMU, in the celebration of the 10 years of IPMU, because I took the PhD there. I was the SPS fellow there. So I have been in the area for a long time, no more than 10 years in Asia this time. And about the talk, most of my recent research has been involved in symmetries in one or another way, either external or internal symmetries. Some of my recent results I can show you later, which are not in the slides later on. About the dimensionality, of course, I didn't include so much that part because it's in process, but I can mention it a little bit. But Yang Baxter for sure will appear. So let's start. This is more or less the content. The initial motivation I got for using Yang Baxter is you see my gun show talk, which I mentioned to you in Strings 2016. I was the second in order in the gun show talk, 5 minutes talking. I was trying to. There was a problem with the counting of Nambu-Goldstone bosons. I don't know if you are familiar with the Nambu-Goldstone theory, but I can explain. It will be explained during the talk. But the idea is that there was a discrepancy between what the theory say and what the experiments say. No? Is the theory say that the number of Nambu-Goldstone bosons or gapless particles emerging in a system is equal to the number of broken generators or dimension of the Coset space. But instead, in some systems, two symmetries corresponded just to one Nambu-Goldstone boson, and the dispersion relation in addition was quadratic and nonlinear, as it's supposed to be for a gapless particle. And then there was this Murayama, Watanabe, and Thomas Browner. They wrote some papers intending to explain that. Yoichiro Nambu himself was touching that problem many years ago. And then I decided to present that in Strings 2016, but by then I didn't include Yang Baxter. It was when I listened to a talk of Edward Witten in that Strings, and he showed the Yang Baxter, and he was implementing, and he modeled he did something like, the Yang Baxter is something like, he modeled like interaction of particles, and then you have obviously it has to be the 3, 2, and the 1. So the lines maintain the slope, no? And I remember he interpreted the slopes as the momentum of the particles. And I was thinking, well, I can take these tools and maybe try to model the interaction of Nambu-Goldstone boson in condensed matter systems. And then when I did it, well, what happened is what you will see in a moment. The problem of counting is solved, and the dispersion relation appears naturally. That's the idea. I will mention, it's not in the content, but I included in the last moment some recent results where I used Quantum Yang Baxter Equations in the neutrino oscillation problem. As you know, the neutrino is a fundamental particle. Particle physics they are fermions, not bosons, they are fermions. But they were thought to be massless for a long time, but it was discovered that they are massive and they oscillate between 3 different flavors. For example, a neutrino is born electronic. You can detect as tonic or muonic after on. And of course, these 3 oscillation between these 3 flavors can be modeled via Yang Baxter. And for the moment, the result seems to more or less match with the experiment. So let's see. Anyway. And finally, I will close with a little bit of gravity, black hole physics, etc., where I intend to implement them, because I have not yet implemented them, but the fact that you can model black holes and condensed matter systems, of course, gives you the chance to use this formulation. So, of course, we start with the difference between internal and external symmetry. Of course, external symmetry, when you say external symmetry, you are talking about space-time symmetries, no? Time translation, space translation, rotation, this kind of symmetries. Well, this is just the Einstein-Hill reaction. When you talk about internal symmetries, there are many. Of course, I will not go in detail into the details of so many examples, but in condensed matter systems, usually we deal with internal symmetries. Then, for example, Hamiltonian in a condensed matter system can violate Lorentz symmetry easily, and that's not a problem. That's not really a serious problem. So the starting point, I will start to explain what is spontaneous symmetry breaking. I don't know if you are familiar with this. Probably mathematics, you also see that, yeah?
Sorry, just to clarify to myself, in gravity, there are just local Lorentz transformations as internal symmetries, or it's more than that?
Well, the Lorentz transformations for me are external symmetries.
Local Lorentz transformations.
Local. Well, those are more at the level of gauge symmetry, no, because they are local.
That they encode different things, right? Local Lorentz gauge transformation are different than the homomorphism.
Yeah. So you are talking about diffeomorphisms are coordinate transformations, basically.
No, I'm just talking about rotation in the frame. Rotation of frame in just one single point of space-time.
So what happened with the...
Well, if you write, let's say, metric in terms of tetrad, the metric is invariant under local Lorentz transformation, which acts on tetrads. And does it count as a local transformation? Sorry, the internal symmetry? Or?
From the perspective of space-time, you mean?
Yes.
Well, normally, when I mean internal symmetries, is that when you're analyzing a system, are symmetries which don't involve space-time from the perspective of condensed matter system. No? Now, if we are going to the space-time itself and we are going to discuss this kind of symmetry, we could start to debate whether they are internal But we are talking with respect to space-time itself. No? Then that will be debatable, of
Some
course.
tangent bundle of space and not any space.
Somewhat?
It's
The tangent bundle.
The tangent bundle.
Sorry.
No, I just.
Housing.
We can talk
We can talk about that later, because anyway. So, I mean, in the case of spontaneous symmetry, Riken has plenty of applications in physics, basically. In material science, spontaneous symmetry can help you to predict the phenomena of ferromagnetism. Normally, the Lagrangian standard has two free parameters, mu square and lambda. Mu square and lambda are the free parameters which you can control. In the case of ferromagnetism, will be temperature and external magnetic field, for example. Then the idea is that depending on the relation between those two free parameters, you can have a single stable vacuum state or a multiplicity of possible ground states. Then you change from your potential could be like this for some combination of parameters, or after for some other combinations could develop this. So you were here very comfortable, but the conditions change. You move here, you are not comfortable anymore, you are trying to find the equilibrium. So which vacuum you select is a matter of the external perturbation. Let's say the external perturbation is the one, the direction of the external perturbation is the one which decides what you select. In the case of a ferromagnet, you go to ferromagnetism, you have before, let's say, high temperature, then you have the domains, the magnets pointing randomly everywhere, that's zero magnetization. But then you decrease the temperature up to some level, up to critical value, such that any small perturbation, in this case a magnetic field, may all the magnets to point in the same direction. This is equivalent to breaking the symmetry of the system spontaneously. And spontaneous symmetry breaking means that the ground state doesn't respect certain symmetries, but still the Lagrangian or Hamiltonian continue respecting the symmetries. That's why I call it spontaneous, not explicit symmetry breaking. That's important to clarify. Then, of course, the biggest example, or the standard example in particle physics is this Lagrangian. Well, normally they put a scalar, but here let's put this index. And the idea is to analyze this potential and the ground state of this potential. Well, this is what I just explained now. This is the multiplicity of ground states when the system reaches certain conditions. And of course, the vacuum condition is obtained and it is given by this. This is obtained if you take this potential here, mu square. Let's put like this v square, or let's put, if you find the derivative on zero, then you will find the possibilities, of course, depending on the relation between. Actually, in this case, if whether mu square is larger, it's smaller than zero. So, if it's larger than zero, it will give zero, trivial. If it's smaller than zero, it will give the multiplicity of ground states. And that's reflected in this potential. And of course, there are ways, this has serious consequences because there is this multiplicity of ground states reflected in this potential. At this level, if you are here, still you are not breaking the symmetry of the system spontaneously. It's only when you receive a small push, then you select a vacuum state. And importantly, if I do a superposition, sorry, I did something
Yeah, you just need to touch the screen. If you touch it, it should go away.
Okay. If you assume all the possible ground states, you recover the original vacuum. This will be important later when we mention some arguments I did recently about Hawking radiation and the information paradox, which I will mention at the end of the talk. Then, of course, the breaking of the symmetry, as I said, the number of broken generators, as a system has certain number of symmetries. And if I break one symmetry, there should be one Nambu-Goldstone boson. If I break two symmetries, it should be two Nambu-Goldstone bosons, and they are gapless particles. Later we will see why they are gapless, why they don't have mass. But this is not the case in certain systems. In certain systems, particularly violating the Lorentz symmetry, non-relativistic systems, this doesn't happen. And it's not difficult to guess why. It's because when the Lorentz symmetry is not satisfied, there is no symmetry between the order of derivatives. No? Derivatives in space and time are not the same order. So it's naturally expected that the dispersion relations are not linear. This Lagrangian here shows that the system, this is the vacuum condition when the symmetry is spontaneously broken is not zero. You know the magnitude of this, but you don't know the direction. So you can select one arbitrary direction. It could have been anywhere, but you can put it here. And then at the end, you can express the Lagrangian in terms of this vacuum, non-trivial vacuum. If you redefine the felts, then you can redefine the felt like this component and then the last component like this. Such that the ground state of this is zero, but the ground state of this is. When you replace, you can guess how many particles become massive, how many particles are massive, and how many particles are massless. This is a standard trick. Obviously, when you see a sigma square, this is a massive term. This is a standard. But there is a more generic way to know the gapless particles. And is this, you expand the potential, zero order. The first order vanishes because it's around the ground state. So in equilibrium, it will not contribute. This is the second order contribution. And this is the mass, the matrix mass of the system. Then, of course, we have said that when the symmetry is spontaneously broken, the ground state represented by this felt, this state particularly, when you apply the symmetries with a unitary operator, the vacuum is not invariant under the symmetry application. Actually, what happened, what a broken generator does, let me put it here. This is the generic ground state. What a broken generator does is when you add, let's assume that the vacuum selected is this one here. Let's call it 0 bar, or better the other side, 0 bar. When the broken generator acts, what they do is to map this vacuum toward another vacuum. So it's like a shift, no? So it's not invariant under the action. But it doesn't happen for all the elements of the group. There are elements of the group which still keep invariant the ground state. So let's say this ground state is vacuum and still is invariant under some subgroup of the large group. And then of course there is a Gaussian space which you can define.
So do you assume that
Yeah.
the Hessian of V is non-zero?
What? The Hessian of what?
Hessian of V
Yeah.
is non-zero.
You mean maximal rank?
So
Maximal rank.
maximal rank, yeah. This is an assumption, or are there any degenerate directions?
No, what happens is that when you, well, this is the matrix, the mass matrix, no? So we are going to prove is that when the symmetry is broken, this has to be zero. The elements of this matrix has to be zero. Yeah, this is the Hessian of this, of the right. All right. But let's say, how do you prove that? Of course, you have to make the group transformation of the Lagrangian. The potential itself is invariant under the application of the group. And then you have to evaluate when the symmetry of the ground state is broken, because you have to expand around the ground state. Then you realize that the only way to satisfy the symmetry is that the matrix elements are zero in that case. Then of course you can expand you have this unitary operator, you can expand at the lowest order in this way. And then you have to act, the important is to see the effect on the Hessian, as you mentioned. And this is the effect, right? And it has to give zero. Then, of course, there are some conserved currents you can define, which are these. This is the electric charge, or let's say the charge in general. And there is a series of things which have to be respected in order to apply the Quantum Yang Baxter Equations. Is first, the algebra structure of the generators of the symmetry transformations. This is the standard definition of vacuum when the symmetry is not spontaneously broken. Of course, the charge annihilates the vacuum because the vacuum has to be invariant to the action of the group. When the vacuum is, well, this is not exactly correct. This statement it's not accurate. It should be like when the symmetry is spontaneously broken. Of course, the charge doesn't annihilate the ground state. Similar thing what happened with, we were talking about that the Hawking radiation can be modeled in that way also. And of course, in that case, the unitary, let's say the action of this, I think this is not completely accurate. What we mean is that when you act this operator over the ground state, it should map the ground state over another state. It's like changing Hilbert space now. Because in such a case, in the thermodynamic limit, all these ground states represent different Hilbert spaces, and they are orthogonal to each other. No? There is a demonstration about that. And of course, there is another parameter. The vacuum expectation of the other parameter is different from zero when the ground state is. But you will see it better with a different notation. But you should know that if this is the order parameter. It's different from zero when the symmetry is spontaneously broken, but it's zero when the symmetry is not broken. This is broken, broken, non-broken. And if you go to this Mexican, but there is a detail here because this is the trick for implementing Quantum Yang Baxter equation, is that if I assume in the case of broken that there is this one, if I assume over all the possible ground states, I mean this possibility plus this plus this plus this plus all the possibilities, I recover the trivial value. It has to be zero. It makes sense because for every ground state here, there is a diametrically opposite state which cancel. So obviously, and these represent 4 triangles of Quantum Yang Baxter, which I will show later. I will show later why is the case. This other parameter can be represented as the commutator between one broken generator and the Nambu-Goldstone field actually, because you can decompose the quantum field in the Nambu-Goldstone field plus the other parameter. There is a way to do that. And then, of course, the vacuum expectation value of the Nambu-Goldstone field is zero, but not for the other parameter. And this equation is exactly this one, without the symmetries. This corresponds to this equation. Well, then, if you assume Lie algebra structure, and we will see later, we can represent this as a double commutator, because you can put this charge as the commutator of the two charges. And then this double commutator will become 4 terms, which will correspond to 4 triangles of Yang-Baxter.
Sorry, what is the difference between phi and phi prime? Again, so you have phi prime and you have phi, not the derivative.
Well, what happened? It will
What
be
is phi prime? What is phi prime?
well, in this case, will be the Nambu-Goldstone field.
What is phi?
What is phi?
Well, phi is a quantum field.
Phi is just some field.
Just some field, some quantum field. Well, quantum fields generically.
But phi prime?
Well, phi prime is different to phi, of course. Phi prime.
What it is?
What happens is that the quantum field, let's put this phi bar, can be decomposed in phi prime plus phi. We'll see that later. Actually, it's a matter of notation. Then, of course, this phi prime is the one appearing here, but this phi is the order parameter. So one is the Nambu-Goldstone field, and this is the parameter. And the Nambu-Goldstone fields, when the symmetries are spontaneously broken, they move along this degenerate ground state. This field move in this direction, while other fields, they move perpendicular because they are massive. They have mass, so they have some gap, right? So I will show you in a moment. I think
some decomposition.
Yeah, it's like here.
Phi and phi prime is some decomposition.
Yeah, exactly. It's like here. Look, phi is phi 1, I times phi 2. So phi 2 is the Nambu-Goldstone field, but phi 1 is the order parameter. So if I apply the vacuum expectation value of this field, the vacuum expectation value of the Nambu-Goldstone field is 0. But for phi 1 is not 0, and that's why the vacuum expectation value of this field is not 0 in total. So it's a decomposition between different.
So you're considering phi a complex field, complex value?
Yeah, it's a complex field, yeah.
But here phi 1 and phi 2 are real and imaginary part? No, or they are.
Well, you can expand, you can make the series expansion the usual in positive and negative frequencies as usual. The Fourier expansion, not the
Well, yeah.
creation and annihilation, as we usually do, is.
No, but I'm asking if I should consider phi 1 and phi 2, maybe ask the other way. Phi 1 and phi 2 are real, or they are complex in your equation there?
Well, this is the best example is with a real scalar field.
Phi is
But you can do it for a complex scalar field. It depends on whether you want to, but at the most basic level, it could be a real scalar field.
But in your equation there, that phi is not real.
No, this phi no, because I am doing it complex. But this decomposition, these guys are real. Phi
So
one and
if
phi
you are
two.
the composition, these are just real and imaginary part.
Okay, yes, exactly. Excellent. So, okay, here, well, normally this is used for the U1 symmetry, which is the simplest one. Everybody knows the symmetry, it's not that complicated. And then, you remember the commutator before, no? The commutator you saw before, this one. In the standard proof of the Nambu-Goldstone theory, where you see at the quantum level, of course you can write the charge as the integration, the spatial integral of the zero component of the current. This is what you usually do. And then you can introduce a complete set of intermediate states using the completeness of the base, this summatory, and then this is an identity. This is an identity, the same here. And of course, this, you can notice the difference between this and this is that this is y and this is 0 is because you're assuming a space-time translation and invariance. Then basically you're writing this this guy is 0 equal to yeah. So you are removing this argument due to the presence of these exponentials here. There is an intermediate state which is omitted, but at the end the result comes out to be like this now. Because the integration in 3 spatial dimensions becomes to be a delta Dirac at the end. Because it's the integral of the exponential theta, it becomes this delta Dirac. So what this is telling you is that in order for this to be independent, time dependent, the time and momentum has to go simultaneously to 0. And when the momentum and the energy goes simultaneously to 0, this is where the regime where the Nambu-Goldstone bosons operate, basically. So let's revise a little bit something here. Let me see. You have this material integral. The first term only is enough. 0, 0, y, and now. So this one is an identity. What you are using is introducing this. That's not a big deal. The subsequent step is simply that you put this like y is time minus is the Lorentzian product.
You want the argument there to be 0.
Huh?
You want the argument to be 0 or not?
Ah, sorry. This is 0. Yeah. Yeah, because we are assuming a space-time translation invariant. So this is a space-time translation. And of course, at the end, this is the decomposition. So these guys become the energy and the mass are the same. That's why you will see m y0 in this side. And in this case, at the end of the day, this partial integration will appear because, for example, you have terms of this form and you will have this partial integration b. This is what made this delta Dirac here to appear. Of course, there are some details to analyze in between and so on, but this is more or less the idea. Because I did this calculation a long time ago, but that's more or less the idea. Believe me, it's right. Then, of course, you understand that the dispersion relation of this has to be linear, but that linear dispersion relation means basically that omega has to be proportional to k, or that the energy has to be proportional to momentum. This means linear dispersion relation. And this is what is always expected. Then, of course, Murayama and Watanabe, they found a continuum rule for the Nambu-Goldstone bosons, etc. And in order to implement the Quantum Yang Baxter Equations, I had to make a series of transformations. So, the other parameter now, for me, would be a bilinear object with 2 index AB, and I will take the vacuum state as another index. And of course, I will adapt what I have before in the same form. The broken parameters, the broken symmetries, will be also bilinear objects with 2 index and k, which can be expressed in this form. is more convenient, more suitable for applying quantum Yang Baxter equations. Then, this is exactly the same expression you saw before. The difference is that now it's written with all the terms are bilinear objects. And this is what I was talking about. This is the space-time translational invariance, which I was talking about. And I think the sign is correct. Well, this is the expansion of energy time minus spatial momentum times spatial y. And that decomposition can be seen here. Now, when you operate, when you expand this double commutator emerged because initially it was a single charge here, but I am assuming that there is a Lie algebra and that these Lebesgue beta symbols are constant, so that they don't influence. Of course, mathematically speaking, it requires some serious analysis in between, because of course this is not always the case that those terms are constant. Well, I am assuming that special case. Well, look at this. When you expand this double commutator, you have 4 terms. You have 1, 2, 3, 4. And of course, every time you commute, there is a minus sign. But since there are the product of 3 terms, you have to introduce.
May I ask one question, Ivan, before you proceed with that long equation? So again, what is QYBE? This Q with the 2 indices. What was?
QYBE.
The Q. Any of these Q with those 2 indices.
Broken.
Would you define it?
Those are broken generators. Those represent the generators of the symmetries, which are broken spontaneously.
I see. So they are like matter charges or no? Matter current?
Generators of symmetry. It's like when you have a symmetry,
How come they depend on X and Y?
you apply these guys here with some parameter. They represent operators.
Oh,
Which-
okay, I'm sorry.
Which
And the phi with the 2 indices?
that's again the scalar field which we were talking about before, which can be decomposed.
Yeah,
In this case,
I'm sorry. Q can be local operators. Like here, like currents are local operators, but Q act on kind of whole coefficients. So that should be independent on X. And because they're conservative charges, they should be independent on T. So I'm kind of still in doubt that this is Mauricio. What is position dependence for charges?
Why Q is position dependent?
no, precisely it's not position dependent. We are assuming space-time translational invariance actually.
So, but then you wrote Q of X, Q of Y, Q of Z. So what is Y and Z?
Well, y represents a space-time point, but of course we are assuming that there is a translational invariance, and that translational invariance is input subsequently. Let's say this is equivalent, no? Because of course you are translating this argument here, and then after you introduce that here, and these exponentials will appear, these guys, and then after, because you have to. Well, I didn't show, but there is a spatial integration here. It's omitted in this, but there is a spatial integration in the spatial y and the spatial c. And then some delta Dirac terms will appear.
But you are symmetry operator. Is what? Q or Q of X? What is your so Q has a function of the space time. Is a symmetry operator or is a symmetry correct? Or what?
Well, it's a symmetry operator. Well, that's an internal symmetry. I mean, the once.
Do you have a formula for this Q in your particular theory?
Well, it could be any symmetry. It could be charge. I don't know. It can represent any symmetry, rotational, or let's say rotational symmetry of the in condensed matter physics, for example. you have all the magnets pointing in one direction. Obviously, I could, in that case, would be, let's say, let's put angular momentum, which is what will rotate this now, or a spin, better, which is what will rotate the system. No? Is the symmetry? It's a symmetry.
Rotate the system, like as you said, rotate the system means that everywhere for every point in your system you do this rotation. It's like
that's a global.
rotation is
That's a
independent
global.
on X.
Yeah, correct.
Rotation is independent on X. So why do you have Y dependence?
That Y dependence is what? Okay. That Y dependence. Precisely at the end, we assume a space-time translational invariance, but we had to put it for being rigorous, let's say. It's a rigorous way, but it doesn't mean that in each point will be different. Because that's why, of course, when it's global symmetry, you don't, it's what happened to what you say, you just rotate all the device. But when it's local symmetry, you introduce a gauge field. What we use is you introduce a gauge field, which is what happened with the gauge theories. That's why, for example, the photon field.
Here, like, the whole talk so far was focused on global symmetry.
Yeah, it's global symmetry.
No gauge fields. So
No gauge fields. And no space-time symmetry. This is no space-time symmetry, but the charge itself is a space-time translational invariance.
But so the Q do not really depend on Y.
No, it will not depend. At the end, it will not depend on Y, because we will integrate. Let's say the spatial integral is omitted, but there is an integral, and there is an integral which will be done. But of course, for a question of space in the paper, of course, I mentioned in the comments that part, but I didn't put the integrals here. But there is an integral where you assume all these things. And when you integrate over the exponential, it appears the delta Dirac. Remember that the delta Dirac which appeared here, look. These delta Diracs here, they come from integrating precisely this spatial portion.
this situation was current itself. Current indeed depends on a position, and your charge was an integral of a current over the Cauchy's line, and that's where you get an integration. But if it's Q, then it's not an integral of a current over the whole space. So then it's not clear why you have an integral if it's really charge Q, not a current that generates the charge.
Don't you want to say that these Q are really current?
No, well, it's a four current. The charges are the zero component of the currents.
It's charge density. It's J naught. It's not the charge.
Yeah, exactly.
Yeah.
Okay, then it makes sense. Yeah.
Okay, yeah. Thank you. Thanks for your comment. Yeah, this is charge density, right?
And the 5 IV?
This
What
is
is the composition represent?
you mean
5 AV. Yeah.
this BA?
Yeah.
Well, it's the same definition we used before. Only that now, of course, it will be analog to this. Look at this.
Yeah.
Only that now I define it as a bilinear object. What's the meaning of the index? Of course, is general. It could be anything. It depends on the symmetry you consider. Because a scalar field obviously only have one component, but this is a vector, it has one. If it's a tensor, well, it could be anything. So,
sorry, is that formula for phi comma a comma b is a definition of phi a comma b, or is there like some alternative? Because phi is two indices is defined through a phi with four indices, and how do you define phi with four indices?
now this N and A live in the same space, and L and B live in the same
Still
space.
some new object phi with four indices. How do I define it? Because in order to define phi with two indices, I need to know phi with four indices.
No, it's like when you decompose a vector, you can, this notation, it's like I can write explicitly the base, or I can just omit the base, let's say. So this is the same, basically. Only that I am showing explicitly the expansion in terms of some bases. But this is a way to remark that this is a bilinear object which corresponds to two different spaces.
Okay, but what is the definition of the phi A comma B?
Well, the phi A B is the same field which we input before, but now generalized.
Before it was just phi.
Yeah, it was only phi.
So there was no A B. So she wants to know what is A comma B.
A comma B are corresponds.
What this indices label?
Well, this indices labels could be anything because it's the only way to match with the notation of Yang Baxter. Let's say one you.
But for spontaneous speech breaking, as you said, there are two kind of types of objects. There is a group and there is a concept, like a group G, subgroup H, and then naturally you have some generators of G, and then maybe some generators of H, or some generators of concept. So if A and B, do they label group, I don't know, subgroup, or do they label like elements of concept?
Wait a second. Could be that this phi AB is like the phi that he wrote as 1 over square root of 2 phi 1 plus I phi 2. That could be one case, one example. So maybe the A and B would label the 2 phi 1 and phi 2 in that case.
No, but it's A comma B, so you can find these two indices.
Yeah, exactly. But if you put
give
it
an
like,
example.
Well, this-
so the A and B would be like the entries of the vector, or the matrix of the vector.
Yeah, so A and B is like a matrix, but I'm not sure which country.
Well, I'm going to tell you something quickly. It's like, first I input a phi, no? It was a scalar, only one component. But here, for example, this guy has many components, and it has an index. So this is an example.
And component, because
Yeah,
it's kind of
exactly.
like O and action, and O and action rotates n-dimensional real space.
Of course, I input now some one more index. It could be anything. It's something general, and it depends on which example you consider. Because whether it's a scalar, vector, or tensor, or something, is you can generalize them. You can generalize the object, but so it's a way to generalize the order parameter to a bilinear object. But of course, if you ask me what represents the index, it depends on the specific physical problem you are confronting, because different physical problems, the components of the field will mean different things, no? Then of course that has no response. Let's say that question has no response.
No, but for example, okay, give me that example, like where phi vector value. What is phi AB?
Well, in this case, one space will be trivial; it will not move.
So you just want to consider rank 2 representations.
Exactly. So I have intent. You
Are
can.
you going to make them irreducible by saying like antisymmetric or symmetric?
Yeah, exactly. You can write a vector as a tensor, no? You can write a vector as a tensor, and you say about the other. This index doesn't move. Only one index move.
Well,
You can.
you just want to say a phi you promote it to matrix value.
Exactly. I promote it to something more general. Let's say.
This is irreducible. Whether you want irreducible, does it matter for you?
It doesn't matter for me at this point. But that's a good question, which, of course, there are many mathematical issues to in between.
The representation can be any, right? This group G can act in any way.
Yeah, but I'm thinking about tensors that some are irreducible.
Look at John. Or tensor product. Yeah. In general, it will be reducible, I see. Okay.
Correct. So then we were here in the promotion to A, B, right? Okay, and we were here. I was explaining that at the end, this double commutator can be explained for terms. No? And it's understandable why there is a minus. I am omitting the partial integration, and I do it by purpose because I want to keep the spatial P, and because that's what will give me the dispersion relation at the end. I mean, I am interested in to know how the momentum behaves when it tends to zero, and how the energy behaves when it goes to zero. When they go to zero simultaneously. And you will see, surprisingly, that when under some conditions, when the two symmetries represent one Nambu-Goldstone boson. Then, of course, the phases group such that the momentum goes to zero quadratically, and the energy goes to zero linearly. And that's precisely what happened in the condensed matter systems. So it seems that the thing is more generic than just phenomenological. No? Then let's well, I delete here for just in case, but you should not keep in mind that there is an integral here, which I don't evaluate, and I keep because I want to keep it. Then these four guys will represent 4 triangles, and you will see later. They will appear like this. Again, this is the vacuum state. So the idea is to analyze the interaction of Nambu-Goldstone bosons. Normally, Yang Baxter deals with 3 particles, no? Or at least 3. You have 3 lines, or in the S matrix case, it's different. It depends which physical system you are considering, but it should be 3. Well, we only have pairs of Nambu-Goldstone bosons. I was interested. So you have 1 Nambu-Goldstone boson, 2 Nambu-Goldstone bosons, and the 3rd particle for me is the degenerate vacuum. The vacuum state is a particle with 0 momentum, 0 energy. And actually, these 3 lines are almost parallel because the Nambu-Goldstone bosons are gapless. They are low energy, long wavelength, basically, limit. So it means that these 3 lines, the momentum is almost 0 and the energy is almost 0. That's why they can move freely around the degenerate vacuum. They don't need any energy to move. Do you have a question?
No, again, what the lines represent? What I should think of using?
1 Nambu-Goldstone boson, another 2 Nambu-Goldstone bosons, and the vacuum state. The degenerate vacuum.
So they are states. So the lines represent states.
The particles.
The line represents particles.
The fells, I mean, you can call it fells. The quantum fells representing the Nambu-Goldstone fells.
Yeah.
Nambu-Goldstone felt.
And what is 0 then?
0 is the vacuum state, this one. Assuming all of them. That's why I was emphasizing what happens if you sum over all the 0 wrong state, no? All the vacuum states. Then will you recover the trivial value, 0. And that will be important because this is precisely what happened in Yang Baxter. Here, for example, you can see this is different from 0 still. But once I put an additional sum here, and I assume the vacuum state, this will be equal to 0. And this is what happens when you sum over all the possible order parameters. This is a way to recover the original ground state, let's say. Okay, and this will be important, for example, in the case of Hawking radiation later. I will mention a little bit about it because the particle number operator when the black hole evaporates is analog to another parameter. So we can also play with that and recover the original ground state. So for the moment, this is the issue. These are a way to simplify the problem because I didn't want to manage so many indexes. So I compactify everything to one index here, etc. And then these matrices are, which is what appears in Yang Baxter actually at the end. I made a correspondence between the R matrices and each object which you saw before. Each object you saw before here. And it came out to be like this. This, for example, 0M, they live in the same space. L and prime, they live in the same space. And A, B0, A and prime L, and so on. I did in this way. And of course, you apply the Quantum Yang Baxter Equations, which is in index notation will be like this. But in component, if you decompose in components, it will be equivalent to this, no? Decomposing the R matrices in this way, in terms of the basis, no? So you will find the textbooks both ways to represent Yang Baxter. One way is this. This is simple because, and this is the other way to represent.
I'm sorry, one question. So what are these states N and prime? What are these states?
The intermediate complete set of intermediate states. which we introduced. They represent.
Okay, that's good. But then how go back to this other? So you have indices A, B. Maybe my A site is. So you have indices A, B, and right 0. So these indices have very different nature. Is that correct? So AV is like some finite index, for example.
You mean here or here?
In all this matrix, the matrix R has 4 indices.
Yeah,
right?
4 index.
So the index N has all these 4 indices. They are from very different vector space.
Yeah, but by rule of Yang Baxter, for example, pairs of index which are in the same column, they have to live in the same space. So they have to represent the same thing.
Oh, okay.
The same apply for the other. So then, of course, you can argue things, but let's say at the end of the day, you have to respect the fact that n prime and L live in the same space, and 0 again lives in the same space. Yeah. So and they represent the space. Of course, each line in Yang Baxter represents one space. Let's say this is one space. This is the other. This is the
One vector space.
okay, one vector space. Exactly.
Great.
So this is more or less the issue. By the time I had the chance, and I was lucky that I discussed this issue with Michio Jimbo. I don't know if he's still alive or not, but it was before COVID. And then, and actually I learned the Quantum Yang Baxter Equations from him directly, discussing in the board. And after that, of course, I knew how to implement it. Then the issue is, at the end of the day, with this simplification I did of the index, this is what I was trying to say. You assume over all the vacuum states now. That's why I put dV. dV is the generate vacuum. It's the generate vacuum. And this equality represents one Yang Baxter equation. This is one Yang Baxter equation. In simplified notation means that I don't consider the internal summatory of n and n prime, but this represents this, and these two equations are equivalent, as you can verify. Only that in simplified notation, I omit some index. Well, I realized that even if you omit those index, the consistency still remains. Then after I made, let's say these four terms here. You see here, 1, 2, 3, 4. They represent 4 triangles, no? Well, of course, by Yang Baxter, they will represent 4 different histories of interactions on Nambu-Goldstone bosons. But by Yang Baxter, those histories are reduced to two independent histories of interaction. So these 2 histories of interactions you see here. If you go through the paper, you realize that each one of these triangles here represent each one of the terms of the double commutator, which you saw before. And of course, by Yang Baxter, you can group the common terms. Some terms can be grouped. And this below corresponds to the case because Yang Baxter doesn't exchange the particles in reality. You keep the same slope, you can see this slope is the same slope here, and this slope is the same slope here. And the vacuum, of course, represents the dot line. 0 momentum is always with the same tendency. This is when you exchange, is when you obtain the other two cases. So it means that the other 2 histories represent just exchange of particles. But like if I do this will be 1, 2. But when I exchange the particles, the Nambu-Goldstone bosons, of course, now this becomes 2 and this becomes 1. Of course, this is not Yang Baxter anymore, but it can have its own Yang Baxter here. So at the end, 4 different histories become 2 independent histories. And the key point is that if these 2 Nambu-Goldstone bosons are equivalent, for example, if n prime is equal to n and they represent the same degree of freedom, I can group all the terms. I can factorize all the 4 terms you saw before. And in this factorization, I can group those phases you saw, the exponential phases you saw before. And in this factorization is where the momentum goes quadratic when you approach to 0. Well,
What are these references to Witten and Costello previously?
this one. This one, well, when Witten was giving his talk, because actually part of this thing was inspired in a talk Witten gave in 2016 in Maastricht, and he mentioned a lot of Costello in that talk. He was talking too much about Kevin Costello the whole time, who also I saw in that conference. And in another in Perimeter, in PI, I met him in person. Quite a nice guy. Well, this is there's a series of 3 papers, but I said the long version of this paper is in this reference, and the referee was Thomas Browner. Actually, was the referee of that paper, who was one of the co-authors with Murayama and Watanabe. No? Then, well, this is in coordinate notation. Initially, I didn't care to write the ground state as a horizontal line, so you could see that I just put the vacuum in any orientation, but you can keep consistency. You can see that this line keeps the same slope, this line, and these are the index you saw, the R matrices. P is here, and you can see N and P appear in the same line because appear in the same column also. So K and N prime, they appear in the same column because they are in the same line. So this is the issue of Yang Baxter. Now you have to keep this consistent of the index here and the fact that they appear in the same line. And this is what happens when you exchange N by N prime. Then at the end of the day, when N is equal to N prime, this is what I was talking about. You factorize. Well, technically you can even factorize these 2 guys, but it's not necessary for realizing that when N is equal to N prime, the phases at the end will give you a cosine of P here and an exponential for the energy. So, and this means that at the lowest order term of momentum which appears here is P squared, and the lowest order term which appears, this expansion is linear for the energy, so it's a quadratic dispersion relation. And of course, subsequently, you could do the spatial integration, but it's not necessary. I mean, if you want to analyze the dispersion relation, you have to keep you have to avoid to integrate in advance, no? And of course, this is when you factorize all the terms. It becomes like this. Then, of course, sine at the lowest order is linear, and at the lowest order, cosine is quadratic in this function. So this means that the dispersion relation is quadratic. It's the way how you approach to 0 in each case, no? What gives you the dispersion relation in these systems. However, when you don't factorize these things, when N is different to N prime, you cannot say that these 2 guys are equivalent. And in that case, there is no factorization except for the Yang Baxter side, and there is no way to obtain or to factorize the phases or to group the phases such that you obtain a quadratic dispersion relation. In reality, you obtain a linear dispersion relation in that case. Then, of course, I verify these results. And of course, the counting problem is automatic because, I mean, immediately here, we are saying when N is equal to N prime, it means that this guy is N, and this guy is N prime. This is a Nambu-Goldstone boson represented by number N, and this is a Nambu-Goldstone boson represented by N prime. And if they are the same, of course, immediately I am saying that I am killing one of the first already. So the counting problem is solved automatically. And I explain why sometimes two broken generators correspond to a single Nambu-Goldstone boson. Of course, more details are in the paper. And Murayama and these guys, they call it type A and type B. That's why I put type A and type B. And of course, it's possible to find a relationship with the rank of the matrices R, which I exposed before. Well, I mean, and this, of course, I have to justify why I can use Quantum Yang Baxter Equations, why I can sum over all the vacuums, and this is what I was talking about before. This is the ground state. If you put yourself on the top and you see the bottom, you see the circle projected here. And if you select one vacuum here, there is a diametrically opposite vacuum, always cancelling. And that's why you can do this superposition over the degenerate vacuum and you will obtain zero. That's the reason why when you sum over all the other parameters, you obtain a trivial result. It's a way to recover the original vacuum state. Well, of course, putting all the possible breaking symmetries now. Or I don't know if the expression is correct. There are different directions where you can break the symmetry. Yeah.
That sum is a little bit strange, no? I mean, shouldn't it be like an integral in general?
Well, you can make an integral, yes, because of course when the vacuums are close to each other, very, very close to each other, it could be an integral, yeah. It should be an integral. Well, of course, in any case, the integral is a summatory. So.
But for example, in the case of the gauge group broken to U1, this U1, this case, this example, what would be the sum over vacuums that you have there? The sum over.
You have ready. Your system generated the conditions already. Let's assume that the free parameters satisfy the conditions where the potential is behaving in this way. Then we zooming this point, let's call it 1, plus this point,
Well, there is a continuous.
plus this. There are infinite points here, no?
Yeah, so it's an integral.
It's an integral at the end, yeah, you're right. And of course, this point has always a diametrically opposite point, which will cancel it. And that's why the sum at the end will give 0.
But typically, when you have infinite sum, in order to get a cancellation, it requires sort of minimization.
Yeah.
Because when you say opposite term will cancel, it usually means that you kind of have one infinite sum, another infinite sum, and to cancel you need some kind of convergence properties. So and kind of mostly this spontaneous symmetry breaking is applicable to continuous symmetries. So it seems that this regularization will be required in most cases.
Well, you say something important. Continuous, because for example, when it's discrete,
you don't have Goldstone bosons.
you don't have Goldstone bosons, basically.
So that's why you
Exactly.
But you just assume the group is compact.
Yeah, but still it's infinite. Okay.
Yeah, that will fix it. I know what you mean, but no, if the group, you assume the group is compact, it will fix it.
I'm still like confused about this first equality. So you have like phi1 bar minus phi1 bar plus phi2 bar minus phi2 bar. So we can see this cancellation. But I don't understand this the second equality. Why is the sum equal to a sum of phi I bars? Because it's clearly phi1 bar minus phi1 bar. So why do you get like second equality?
So what you mean is that this doesn't represent the fact that there is a minus after the, well, because anyway, in reality, they are supposed to be independent, only that by chance, or not by chance, of course, by the symmetry of the ground state itself, I can call this phi 1 here, and let's call this phi n here. Well, phi n comes out to be equal to phi 1. And then phi minus 1 comes out to be phi 2, and so on and so on and so on. So it comes out to be, or n plus 1 actually, n plus 1. It's a there is a periodicity. There is a periodicity implicitly here.
What is 0 dB? The 0 dB, what is that?
0 dB is the generic vacuum. What happens is that when you sum over all the, I am emphasizing that this is the generic vacuum. Before the symmetry is broken, the vacuum is degenerate, but I must clarify that once there is a small perturbation, a tiny perturbation, which in the case of a ferromagnet will be a external magnetic field, in the case of other system might be something else. There are no multiple vacuums anymore. The system just select one. And then I cannot call it the generic vacuum anymore. No? That's why I call it single vacuum in this case. So that's why I emphasize between dB. When I put single vacuum, you will never see a sum here. When I put dB, the generic vacuum, I always sum. I put a summatory of all the vacuums. Yeah. Any other questions so far? Okay.
But that's not really a vacuum because it's not minimum energy. So probably what you mean is just the continuous linear combination of broken vacuum.
Well, it's minimal energy vacuum. What happens is that there are many vacuums which have the same energy, minimal energy.
So you just take the continuous linear combination of all of them.
Exactly. Yeah. Well, this is another issue. It's just to demonstrate that those vacuums are orthogonal. This is a generic demonstration of the orthogonality vacuums, but I will skip it because I think you know it in advance. But you should know that in the thermodynamic limit, the ground states are orthogonal to each other, no? So, and they represent different Hilbert spaces. Now I jump now to how to apply Yang Baxter. This is completely new, no? For those who are not familiar, as I mentioned, Weinberg, and Glashow, they obtained the Nobel Prize of Physics for the electrowave theory, the unified electromagnetism and the weak interaction. They did it by gauging some symmetries. They used the Higgs mechanism, and they obtained the boson C and W from the theory, from gauging symmetries, and they obtained the masses of those via Higgs mechanism. Boson C and W, also the mass of the electron. However, there are defects. Of course, the theory is not accurate because it cannot predict the mass of the electron. There's some freedom, etc. But the point is that the neutrino was assumed to be massless by the time. The neutrino was a particle difficult to detect, and it was detected because there were apparent violations of the energy momentum conservation in certain processes. Then somebody was proposing that the energy momentum conservation should be modified. There were these proposals by the time. But fortunately, somebody said, no, there must be a hidden particle. And that was the neutrino, which was discovered, difficult to detect what they discovered. But the surprising about neutrino is that there is a famous problem called the solar neutrino, which is that they knew that I think the sun generates electronic neutrinos. And they were expecting certain amount of electronic neutrinos to arrive. But they obtained much less amount of neutrinos than what they expected from the theory. And the reason is because the detector was settled for detecting only electronic neutrinos. So the other flavors were ignored. Well, it came out that the reason of this deficit is that the neutrino oscillates. So some neutrinos which started electronic became tauonic or muonic. So, and this was unusual, this oscillation. It comes out that because of this oscillation, the neutrino has mass. Well, I will focus just on the oscillation part. It's a problem which many people have focused, and this matrix you see here, where C1, C12, C is cosine of theta 1, 2, S is sine of theta 2, 3, and so on. This is the notation. cosine and sine. This is actually a rotation in a three-dimensional space. Nothing mysterious. And it represents the flavor oscillation. And the parameters, of course, are the mixing angles. There are some CP violation parameters which I don't include for simplicity, because of course I wanted to analyze the simplest scenario. And of course I know in mathematics people don't care the experiment so much, but I have to mention this is that there are two contradictory results between the experiment of Kamioka in Japan and the experiments from these guys in Fermilab. I think Fermilab obtained 0 CP violation, and I think Kamioka obtained maximal CP violation. They use different methods, but both of them are serious, and they obtain completely contradictory results. About the mixing parameters, most of them they agree each other. And I was concerned about finding an explanation about this oscillation. Still, this doesn't explain the mechanism of origin of neutrino masses, but my perspective is that the neutrino being so weak, interacting so weakly with anything with a so small cross section, is permanently shifting between 3 different vacuums. So in this picture, instead of having the Mexican hat, you have a three punctual, 3 well-picked ground states. Well, you know how to, let's say, imagine the Mexican hat, but only with the chance of going to three points. So when the neutrino flies, is shifting between a vacuum where it identifies itself as an electronic, then to a vacuum where it identifies itself as dionic, and then go to another vacuum where it identifies itself as muonic, and never breaks the symmetry. So in this picture, this is a model. It's a model. The idea is that the neutrino never breaks the symmetry, never selects any defined ground state, but it's not a boson. It's a Fermi. So that's another difference. And why I'm taking serious or more or less serious is because in this picture I will explain a little bit. I define, of course, the ground states for the electronic case, like this. This is the ground state. And this is the expansion in the different flavors, because this is a change of flavor, right? Then the idea, well, this look a little bit, I didn't see it in that way in my file, but anyway. This is the same expansion. This is electronic monotonic expansion in 3 different labels, 1, 2, and 3. Because of course in the neutrino oscillation, you have 3 flavors, but also you have 3 numbers which we call eigenvalues. Then you can define that the mass, for example, the mass 1 is a superposition of the mass of the neutrino electronic plus the neutrino muonic plus the neutrino dionic with some weights, no? Like in quantum mechanics or that. So in other words, this is a decomposition of the ground state for each flavor in terms of the ground state defined by the.
Sorry, but in standard model, electronic, muonic, and tonic neutrinos are different particles described by different quantum fields. Whereas here, would you say that they just different vacuum states, but not the same field, or what do you mean?
No, it will be the same field. Obviously, it will be the same field, but of course, a quantum field, depending on the vacuum where it remains, will behave different. No? Will identify itself as different. It can happen. It's like this crazy theory that says that if our universe decay in a different vacuum, we stop existing, or this kind of issues, more or less similar. No? So obviously, but in this model, in this idea, the neutrino is a single field. You can expand as a fermionic with the fermionic expansion as usual.
So this doesn't come from the standard model.
No, the neutrino is from the standard model, of course, but
You are proposed that
this is not the standard model, because the standard
cannot be.
because the standard model doesn't include the oscillation. No, The oscillation is something which is outside the standard model. And actually, because it was discovered subsequently, the standard model was done. So this is where the standard model started to fail a little bit, the standard model of particle physics, and there is no serious theory proposing a mechanism of the origin of mass of neutrinos, different to proposing that there are heavy partners or the stereo neutrinos, or the only way that the Higgs mechanism gives mass to neutrinos, I think, is proposing stereo neutrinos or something like that, which is what Weinberg did. Weinberg proposed that idea, but nobody has seen them, nobody has detected them. And as far as there are only 3 flavors in the measurements of neutrino, then let's try to play only with 3 flavors to see what happens. And the reason why I'm taking this serious is because if this is true, the neutrino really oscillates between the 3 ground states, it should satisfy this condition. Again, the same, no? The superposition of all the ground states should give me 0, in the sense that the superposition of all the possible order parameters should give me 0. But going that way means that these quantities should be 0. This comes from assuming this component plus this component. So when you see 1, you assume this plus this is this equation you see here. And you apply the same for the level 2 plus this is this equation. And for 3, then and the first 2 equations, I found out that they are equivalent only shifted by pi12 in the mixing angle theta 1, 2. Then, of course, they don't give any new information. And then I apply Yang Baxter equations. In the case of course, this is not accurate because I found that the mixing angles, they don't assume, let's say, the double of the mixing angles, because these are the mixing angles, but multiplied by 2. I approximate that soon to 180. Yeah. Yeah.
Is this change of base is given by the mixing matrix?
Yeah.
Did you say that the mixing matrix is a rotation?
Yeah, it's a weighted.
The determinant is 1.
Yeah. It's orthogonal.
But then, isn't the equations that you wrote on the next slide, doesn't that imply that, say, the first column sums up to 0, and the second column sums up to 0, and the third column sums up to 0? That means that there's linear dependence in the matrix. And the determinant cannot be 1. How can the rotation be determined 0? That's what I don't understand. Yeah, that's what I'm saying.
Well, that's a good point. Is there is
Can be 1, it's equal to 0.
Yeah, it's a stronger state, it's fine. But it definitely can be 1.
well, that's a good point. I will have to investigate further, but it's true what you say. The determinant is orthogonal. The determinant should be 1. That's right. Well, as I say, this is an approximation because at the end, the sum of the angles is now 180, as I mentioned. And in addition, let me think, 2 equations are redundant, so.
Okay, maybe I'll ask you a question. So the mixing matrix, it's measured experimentally to some extent.
Yeah, it's experimental. They found experimentally this connection between, because
What's the experimental determinant of the matrix? Is it close to 1 or close to 0?
well, this matrix, the experiments determine that they calculate the mixing angles, theta 1, 2, theta 1, 3, theta 2, 3, but they, of course, some ranges, no? They're not exactly. And this, of course, it should be a rotation for any kind of angle they obtain, so it doesn't matter. And the other is the masses. They calculate M1, M2, and M3. Actually, not M1 and M2 and M3. They cannot be calculated for any reason. The experiments can only calculate delta M1, 2 square, delta 1, 3 square, and delta of the deltas. No, and there are 3 possibilities. Normal ordering is what M3 is much larger than M2, which is close to M1, which is the more probable. This is normal order. The experiment calculate with 1 square, which I think is m3 square minus 1 square. And they calculate also delta n 1, 2 square. Or the opposite, 2, 1. They calculate these differences. So in other words, these experiments are part of the neutrino mass problem is the following, is that you cannot calculate, they cannot determine experimentally why is M1, why is M2, why is M3. But they can calculate only these differences, and this provides some freedom still in the setup. No? In addition, the mixing angles are not well estimated yet. And of course, there are some parameters which are don't include yet, which could be the reason, could be a good point for exploring what you say. I mean that they might create this deviation with respect to the determinant being 1, for example, in such a case, which are omitted here for simplicity. But yeah, that's a good point, and I appreciate the comment. But then for putting in this way, this is just approximation, of course, and this is a way to put the mixing angles. Again, these are the 3 neutrinos, and again, you can apply the same. And of course, I don't show here the results, but because I didn't want to extend that much, but they are more or less close to the experimental observed value. So that's why I'm trying to take.
Observations of what?
Huh?
Which results are close to which observations?
The results of these calculations under this approximation using these conditions.
So those conditions before those you impose.
Yeah, those conditions impose.
You okay.
Yeah, those impose. And of course, plus the condition given by the triangles, because these triangles, well, I put in this notation, but this is these lines represent 1, 2, 3, also 1, 2, 3. So of course, there is a relation between the masses 1, 2, and 3 and the mixing angles. You can play with trigonometric arguments with a Pythagorean approximation, which is not accurate because it's not exactly a triangle rectangle, no? And it's not even necessarily a triangle. No? It could be something else because it's not necessarily 180 degrees. Where under such approximation, the results are more or less within the range of the observations. Not exactly, I cannot say is the observation, but because there are some huge uncertainties still in that.
So, like which observations? Observations of neutrino oscillations? Are you claiming that you derive?
Oscillations, yeah. Yeah, but the neutrino oscillations they don't tell you N3, N1, or N2. They give you these differences. They give you delta N3, 1 square. They give you this value is observed. And they give you theta 1, 2, theta 2, 3, theta, all these values they give to you. There is a discussion, a debate, whether I think there is one angle, I think theta 2, 3 is near 45 degrees. That's why I approximate in this way the triangle. But of course, it could be different to 45. So the experiments still don't define whether it's 45 or not.
So also, what is this? Where is this Yang Baxter equation coming from? I thought before you had continuous symmetry importantly, right? And here you seem to only have 3 vacuum, right?
Here you bring to
Well, of course, it's a different problem. This is a different problem because this is not the spontaneous symmetry breaking problem we were looking for before. This is the neutrino oscillation problem. I'm just trying to see how to implement in this setup the scenario of quantum Yang Baxter.
But why you apply quantum Yang Baxter equation to get this kind of identities? Why you apply?
Why Yang Baxter? Okay, why?
Yeah, why?
Well, that's a good question. Simply that when I saw the that there were three flavors. Investigations, deep investigations in the matrix. And playing a little bit with the triangular relations, I found that there were some interesting correspondences between the mixing angles and the value masses of the neutrinos, M1, M2, and 3. No? Not the mass of the flavor, but take into account that M1 is a superposition of three flavors, M2 and M3 is a superposition of three flavors. Then I was thinking, well, maybe if we can model the response about Y is because in this setup, if it's true that a neutrino is flipping between three different ground states, 1, 2, 3, three different ground states without breaking the symmetry, and that's why the Higgs doesn't give mass to the neutrino, because the Higgs doesn't give mass to the neutrino. Then, of course, Yang Baxter could be applied here because it worked. Yang Baxter worked in the previous problem when the symmetry was not spontaneously broken yet. Because, Yang Baxter is an issue where I have to sum all the ground states. I have to do superposition of all the ground states. And when you sum all the ground states, you are not breaking the symmetry yet. The symmetry is broken when you select only one ground state. But if a particle keeps flipping between all the ground states, it's not breaking the symmetry. Then this is where I was thinking that Yang Baxter could be applied. It would be like summing all the ground states again.
Previously, you state phi is general enough, then you define R matrix via this phi, and in that case, those vacuum are continuous.
In that case, we're continuous. Yeah, that's true.
And
here are not continuous.
And you state that they all follow this commutative relation, like R equals to R, or whatever case.
The three flavors, the three flavors. I am imposing those conditions over the three flavors: monic, tonic, electronic. Yeah. Well, of course, I use the other base because these matrices are done in the base 1, 2, 3, and 1, 2, and 3 are combinations of flavors. So, because of the mixing matrix, let's put it this way: this matrix makes basically the flavors, and you can see it here perfect. This flavor, and you can make the inverse of this matrix. You can make the inverse and also write phi 1 and phi 2 and 3 as combinations of these three guys. So these triangles in reality are expressed in the base of 1, 2, 3, not in the flavor. And actually, it should be more properly an oscillation between the three eigenvalues, and not oscillation. Well, it's equivalent. Oscillation between flavors is just equivalent to oscillation of the three eigenvalues. The point is that I predict values of N3, N1, and N2 explicitly, and it comes out that the N3 predictor is much larger than N1 and N2, and N1 and N2 are quite close, and stay inside the range of values predicted by the experiments. And the angles are also within the range of the experiments. Then, of course, there must be something good behind, but still, of course, there are some mathematical issues to explore, like the one addressed by him just recently. Well, the Y is simply because the neutrino doesn't break the symmetry. And then since it keeps flipping between the three ground states without breaking the symmetry, then of course, from my perspective, that's where you can apply Yang Baxter. In the previous one, there was symmetry breaking, spontaneous. It's true, but the trick was that all the calculations I did were before I break the symmetry. When I sum all the ground states, I can do that when I am not breaking the symmetry yet. But once I break the symmetry, I cannot sum over all the ground states. That's another issue important to notice. So Yang Baxter, I cannot use Yang Baxter if the symmetry is broken. After the symmetry is broken, it's lost. It's lost Yang Baxter.
Sorry, but I have to leave.
Sure.
Thank you for the talk. Thank you.
Sure. Take care.
I don't see where you can get three particles out of a single quantum field. Like if you have a field with multiple vectors, you can have in this part of space-time it lives in this vacuum, and then another part of space-time it lives in the other vacuum. Maybe there's the main wall between them, but how can you? So there will be this particle with these properties in this part of space-time, particle with different properties in this part of space-time. How can you have all three simultaneously? I don't see.
You mean the neutrino flavors?
Yes.
No. What happened is that, I think, I understand what you mean. Somehow, from this picture, when the neutrino is moving through space-time, it feels in some moments the growing state as it feels itself as electronic itself, and in some portion of space-time, it feels itself as muonic, and it feels itself as tauonic in some portion of space-time. But investigating why, it could be there must be a deeper argument behind that. Remember that the vacuum is a complex institution. No? The vacuum also has secrets. It permanently creates and destroys particles, etc. So of course there must be something deep behind to explain, and that's a good point which we are addressing here. Why a neutrino will feel sometimes. It's like you are sitting here and you feel a human, and then after you move a little bit, and then you transform in some, I don't know, a giraffe, or I don't know, any animal you want to imagine. Well, why does it happen? That's a good question, but I have no response to that question right now. But this is the way I model that part. Now, coming to gravity, which is the part, I will skip a few things because, of course, it's so long that some people I know. But I will mention the most important. In looking into the black hole information paradox, I will go directly to the Hawking radiation. And for that purpose, here. Well, I will mention a little bit about quantum depression at the end, but let's say in Hawking radiation, what Hawking did was to compare two vacuums, no? One before the formation of the black hole and one after the formation of the black hole. And he did it via Bogolubov transformations, of course. In agreement with one observer located at infinity perceived, you can define a vacuum before the formation and a different vacuum we call bar after the formation. Well, then of course, when you expand these terms in terms of the previous modes by using Bogolubov transformations, then you will find that what you believe was vacuum is not vacuum with respect to the other modes and so on. And this is what Hawking did, and that's why you have, for example, this result here. You have in the path null infinity a scalar quantum field expanded like this, via the dagger. And you have, I think this is before the formation, this is after the formation of the black hole. You have a dagger and this CC dagger are those who go inside the horizon and nobody see. And these two guys have the same information and so on, but I can relate these two set of modes via Bogolubov transformation, as they say. And the notation used here is because already I used the quantum depletion approach. The point is that at the end, Hawking obtained this spectrum of particles, and that's the Hawking radiation. So I have a way to express Hawking radiation via symmetries, symmetry arguments. And the argument is as follows. Let's go here better. Okay, I will show this Lagrangian after, but let's start from here better. In the Hawking picture, of course, the idea is that antiparticles are created, and then randomly, arbitrarily, the antiparticle enters and the particle.
Unfortunately, particle and antiparticle, both of them have positive mass.
Right.
So that's why if antiparticle falls into black hole, the black hole still grows. Particle falls to black hole grows. But in Hawking radiation, the black hole should decrease in size. So therefore, it cannot be explained by particle-antiparticle.
Well, in the rigorous, in a rigorous level, no.
Even in any level, it can be explained. That's the key difference between charge creation in strong electric field and case of black hole. Because for a strong electric field, like particle with a negative charge can do some work on the field and decrease its energy, and therefore kind of compensating for 2mc square created of kind of energy of the particle. But for black hole, unfortunately, such mechanism is not possible because antiparticle it has
Also positive energy.
It has same positive masses, and the black hole mass will just increase by a mass of antiparticle. So therefore, like this mechanism need to be significantly modified.
Sure. I understand you, but also take into account that there is a flip in the signature now of the space-time. No? When you cross the standard coordinates become space-like. I mean, the space becomes time, and time becomes space. Then that might be the reason because of which the arguments of energy have to be reformulated, no? In that sense. But still, I understand your point, but of course this doesn't affect the
But then at least if you want to use this argument, your picture should at least emphasize that the antiparticle is inside of the horizon. If you want to use this argument about kind of some change in definition. So while your picture you depict them outside of the horizon, and
no.
that really contradicts with
yeah.
our understanding of
Because-
just
Yeah, thanks for the comment. What I mean is that they are randomly created around the pairs, and suddenly, accidentally, it can happen. The one falls and the other. Now the question is why always the antiparticle falls? Why not the particle, for example? That's a good question. That's a flaw in the argument also, in the argument, okay, which I mentioned also in the last paper. Well, let's say the issue is like this. The particle number operator, which when you see the Hawking calculation, which is actually, let me jump a little bit, because there were many slides. I think I put the Hawking, this is the Hawking calculation, no? Because this is the Penrose diagram, okay? The future, null infinity, etc., the horizon, and so on.
Sorry, unfortunately, this diagram is a diagram for what is called external black hole. So on this diagram, black hole exists forever. So there is no anything before formation or after formation. It's just a space-time where black hole sitting in the middle of space-time.
Yeah, well,
so this diagram has nothing to do with black hole formation.
Yeah, no problem. And still, of course, the arguments I will explore are not affected by that, but still each point represents an event.
Okay.
So, of course, in certain points, you can represent certain events, and in others, other events. You can close to the past null infinity or the future null infinity, and those represent past events, future events, and so on. So anyway, this is the expansion, the past null infinity. This is the expansion. This is what I was talking about. And of course, Hawking found this relation, basically. This is the vacuum before the formation, but after the formation, of course, when you apply this vacuum condition, you find that the coefficient of the Bogor, which makes the positive and negative frequencies, is non-zero, and that's why the particles are created. And that's the difference between a curved space-time and a flat space-time. In curved space-time, you will never see mixes of positive and negative frequencies. For example, you always span a quantum field with positive and negative frequencies, and that's not a problem. It will be like that forever. But in curved space-time, there are mixes between frequencies, and that's what generates the Hawking calculation. There are analog processes in condensed matter, which I will just mention briefly. It's called quantum depletion.
Actually, you don't really need curvature, right? Like there's this thing called the Uru effect, You just need to have a non-inertial frame.
What?
You just need to have a non-inertial frame. You don't need curvature of space-time.
Also, the Unruh effect, no, an accelerated frame also, Unruh proves subsequently.
It's the same.
Exactly. Well, of course, there is. Exactly.
It's principle of general relativity.
Exactly. Well, I mean, before talking, mention a little bit about quantum depression, the idea is that I found the Lagrangian, that this Lagrangian here reproduces the Hawking radiation. If you have this potential in this form, with a quadratic term, the particle number operator, cubic term, and 4 order term. The difference with respect to the one we saw before is that now there is a cubic term here. When you find the Euler-Lagrange equations of this in the kinetic terms, you will obtain the Hawking radiation for some combination of parameters. So that's why I interpret the mechanism of Hawking radiation as a mechanism of spontaneous symmetry weakening. And what's the symmetry under consideration? Well, let's analyze. If you have a black hole, the evaporation, the black hole has mass, charge, and angular momentum. This is what we know. You can, the entropy of the black hole, which is proportional to the area of the horizon, measure the amount of information hidden behind the black hole. And of course, you can make as many possible changes of internal configurations as far as you keep mass, charge, and angular momentum. That's a symmetry for the black hole. You can change, you can make as many changes inside if you keep mass, charge, and angular momentum. That's the symmetry which I am considering here. But once that symmetry is spontaneously broken, of course, is where and it can be proven that when it's not broken, of course, derivative of B with respect to n equals 0, we obtain the trivial n. It's very easy to see why n can be trivial because there is always a factor of n after the derivative. But there are some combinations for which this n is non-trivial and it comes out to obey this equation, which is equivalent to what we perceive in Hawking radiation. So then, what I interpret is that the black hole, from the perspective of symmetries, is a system breaking spontaneously the symmetry under exchange of configurations inside, and that's why it has to emit particles, and it's permanently trying to look for an equilibrium condition which never finds. In other ways, the black hole is always an unstable system. And that's why the Hawking radiation appears. Well, Hawking radiation is some kind of instability, not the same instability we see in the classical black holes, but it's some instability. So this is the arguments, of course.
I might be wrong, but there are many people who can correct me. Isn't it origin of discussion that software?
The what?
Software.
Software.
It was a bit appeared from the breaking symmetry, and it was originated from Goldstone modes.
Who wrote that? Who is the author?
Still wrong? Okay.
Well, there might be similar arguments, but I didn't see anybody really before proposing that the Hawking radiation was due to a spontaneous symmetry breaking. Well, actually, that's a question I did.
Last paper of Hawking.
Yeah.
One paper of Hawking?
Last paper of Hawking.
In which year?
The 3 last papers.
3 last papers? Really? Well, I will take a look. It would be interesting to compare because I didn't check it. Well, so he claimed that the black hole evaporation comes from spontaneous symmetry breaking. Well, I have to see what kind of symmetry he's considering, if it's the same, or if it's the same Lagrangian, or... Because one argument the referee had when I submitted the first time to a journal, which was rejected, it was rejected initially from European Physical Journal. The argument was that this Lagrangian not necessarily connects with gravity. Is what the referee said, oh, it's correct, but what do you claim that is gravity then? What I did in the paper is to demonstrate, of course, that you add some terms in the Einstein-Hilbert action, and actually there are some theories where there is some potential terms, which assume cubic, quadratic, and whatever. And when you made the perturbation theory, which it doesn't have to be perturbation because it's a strong field, but there are ways to input the strong field approximation there. I found that there is a correspondence with certain modifications of gravity already proposed in the literature, particularly with massive gravity in the version DRGT, because they did a resummation also in expansion terms. Then I claim that massive gravity is not the theory for solving that energy, but it could be connected with perhaps the origin of Hawking radiation, for example. Then I found that, but the referee was not so convincing in European Physical Journal-C, and that's why I didn't get it there.
That massive gravity was pushed by Mokhtar Hassan for 2 years and then they gave up.
Yeah, exactly. And then, well, it is true, and this is what I want to see your comments, because if this is true, it's true that the particle number operator is 0 before the formation, and it corresponds to spontaneous symmetry weakness, then of course it can be seen as an order parameter somehow. So if it's an order parameter, one way to recover the ground state is to sum over all the possibilities. But if you do this, some expectation values will be negative. It's the only way to recover the original ground state. So it means that my interpretation is that the black hole should emit not only particles but also antiparticles. And maybe that's the trick or the key way to recover the information. I don't know. So I want to see maybe your comment about it. You can say something, or this is one thing.
I would say there is a major problem. Like if you are talking about Goldstone bosons and all these Goldstone theorems, so as you like showed before, the Goldstone bosons should have 0 momentum, because that's the only way to satisfy that non-zero relation property. So and then that means that they carry like no energy. So that's the only way for them to be like similar to vacuum state. So and for Hawking radiation, you really want your particle to carry some energy. So even in that paper by Hawking, where they don't explain the black hole evaporation, they explain the black hole entropy. So it was still like counting some soft hair, but this soft hair was not carrying any energy. So it was just counting some states, which are distinct states due to symmetry breaking. So it still was kind of calculation, not of evaporation, but of black hole entropy. So, and in your calculation, there is kind of contradiction that normally you expect that Goldstone bosons do not carry any energy, while in a Hawking radiation, you basically have like a particular value for energy flux, because that's kind of set by temperature of the black hole. The black hole like radiates as a black body with a Hawking temperature. So that means that the amount of energy it radiates per second is area of the black hole times sigma times t to the 4th. So and because each Goldstone boson carries like 0 energy, so it kind of contradicts with positive finite amount that is radiated Hawking radiation.
Yeah, well, this doesn't mean that the particle numbers operator, which represent the Hawking radiation.
I'm not sure about particle number operator as well, because like most of the Hawking radiation will be just electromagnetic radiation, because temperatures are usually so small that you hardly can create any particle. So most even it will be electromagnetic radiation. For electromagnetic radiation, there is no notion of particle number operator. There is no such thing as number of.
Yeah, well, let's assume we focus on Hawking radiation only, and we care only for Hawking radiation. In such a case, this is not necessarily claim that the particles emitted are Nambu-Goldstone boson. They are not necessarily Nambu-Goldstone boson.
But the theory was completely about Goldstone bosons, like all these equations you can supposedly derive in the context of Goldstone bosons.
No, because there are two fields. Remember the decomposition. There are two fields. The field is decomposed in the Nambu-Goldstone field, plus the other parameters. So what I'm claiming is that the particle number operator here is the other parameter, but the Nambu-Goldstone field is something else. It could be, I don't know, in the surface of the event horizon as G at the valley center, because the valley has some arguments also that the entropy is proportional to the number of Nambu-Goldstone bosons in his analogies with condensed matter systems, for example. But in this case, no, I am not connecting the radiation emitted by the black hole with Nambu-Goldstone bosons. They are not, they are other parameters. And the Nambu-Goldstone field is not the other parameter in that case. So, but yeah, your argument, I understand what you are trying to say. The other issue is, well, I think this will be all, but let me say something final, because I wanted to mention that as a motivation that there are some analog models in gravity. People have done some analogies, and the best slide is this one. In condensed matter system, there is a phenomenon called quantum deflection. This is a final issue, which is analog to the emission of particles by a black hole. Because in condensed matter systems, some fluids, of course, at zero temperature, they shouldn't be able to emit particles. Well, still via quantum effects, it happens. Now there are emission of particles, and that's called quantum deflection. And it has a formulation. I did a publication about that in this journal, which is the World Scientific Journal. And the starting point is this Hamiltonian. So you have this kinetic term, and this is the interaction. When you diagonalize the Hamiltonian, you can connect certain modes, and this set of modes. And you obtain and explain the expression of quantum deflection, which is analog to Hawking radiation. So, I mean, this is a way to connect a condensed matter system with the physics of black hole, which I think is interesting for those guys working in holography and so on, because holography people don't necessarily talk about Hawking radiation. No, they never touch it because it's another issue, but there are different kinds of holography, not only the ADS-CFT of Mardasena, there are other proposals. And with that, of course, this is the formulation, the weakly gas, the dilute gas and approximation, etc. Of course, there is thermal, but the same things, and you can compare with the Hawking issue. So I just want to conclude. There are some results I didn't show here, which deal with symmetry, which are my most recent results about dark energy and dark matter. I claim that I obtained the value of the vacuum energy observed via symmetry arguments. There are symmetry constraints coming from the spacetime itself, which suppress the ultraviolet modes. Also, I found that the dynamic of the galaxies, or what people call dark matter, comes also from deviations of spherical symmetry. That's another idea which I didn't show here because I didn't want to. I wanted to focus more on the Yang Baxter issue and other issues. Well, most of my research is focused on symmetries. Then the conclusions here. Now, the Nambu-Goldstone theorem is a natural consequence of the constraints coming from Quantum Yang Baxter Equations. And the same constraint illustrates the generic character of this. Take 1 and take 2 are only those who have linear dispersion relation and those who have quadratic dispersion relation. I didn't talk so much about this part, but there are some arguments of an alternative holographic approach suggest that the black hole is a critical condition, and it's analog to a system which has a perfect way to store information. Let's say, that might be interesting for you, but I didn't mention here is that there is an analogy between the way how the black holes store information and the way how the neural networks store information, for example. And the black hole seems to be the most ideal system. Let's say they can store information in a perfect way, and there are mechanisms analogy to neural networks. Quantum depression corresponds to the Hawking radiation. For me, this radiation is just a spontaneous symmetry breaking process continues. No? So the black hole tried to find its growing state condition, but fortunately, again, feel stable and continue decaying continuously. That's an issue. the quantum Yang Baxter, well, these four conclusions, well, I wrote down, this four conclusion is not accurate. Actually, that's not correct, because the gapless particles actually are in the at the event horizon, which is what precisely you were talking about. Well, this might be confusing. The quantum Yang Baxter equation can help us to solve the neutrino mass problem, and I think, well, there was one more slide, but it doesn't matter. The issue is, any other question, comment?
But you are done.
Yeah, I am done. Okay. Well, this is not correct. Actually, the modes. No, this is not gapless particles actually.
I think we had several questions during the talk, so let's thank Ivan again, and then you can continue questions.
Yeah, we're gonna continue discussing after.
You are here until tomorrow, until Saturday, so
Yeah, until Saturday. Here, if you have. Well, it was 2 hours talk.
Yeah,
It was longer
a
than.
little bit longer than I expected. That's okay. That's okay.
Yeah.
Let's thank Ivan. Fine. Okay.
Thank you very much.
Yo te mando un mensaje.
Ahora,
Tengo que-